Okay, cool. So it is my very great pleasure to introduce Professor Andrew Biewener for today's seminar. Dr. Biewener is the Charles P. Lyman Professor of Biology in the Department of Organismic and Evolutionary Biology at Harvard University, and he's the director of the Concord Field Station. He's also a fellow of the American Association for the Advancement of Science. He earned his Masters and Ph.D. under the supervision of C. Richard Taylor and Thomas A. McMahon, and was a professor at the University of Chicago for 16 years before he went back to Harvard. His work focuses on the comparative locomotor biomechanics of mammals and birds, in particular studying the neuromuscular control of walking and running and flight, and also the phenotypic plasticity of musculoskeletal systems from both an evolutionary and an ecological perspective. So today, Professor Biewener is going to talk about some of his recent work over the last few years. And so without further ado, I don't want to take any more time. I'm just very pleased to welcome Professor Biewener, and please take it away.
Okay, thank you, Kathleen. That was quite the comprehensive summary. At my phase of the career, I guess I've been doing a few things, and I also admit that some of this work is more recent, and it dates back a decade or more. So I'm trying to do the things that I'm trying to work on as I sort of wrap up my career. So the talk today is going to have really two parts. It will be fairly broad. I'll pause after we finish with the first part, which is going to focus on muscle function, measuring muscle function in vivo, and using those methods to study how animals can move robustly and maintain stability under challenging terrestrial locomotion conditions. And then the second part will be the work we've been doing having to do with how birds maneuver through cluttered environments relative to collaborative work with people trying to control UAVs for navigating and robust control of movement in flight. And so the people that really did a lot of the work, Monica Daly, who's a graduate student now, is an associate professor at UC Irvine, and then her PhD student, Joe Gordon, who's a veterinarian, has gone back to veterinary practice, really did a lot of the work on the in vivo muscle function that I'll focus on with the guinea fowl, and that they're shown down here, over here on the left, some of our earlier experiments. And then the second part of the talk will be focused on the flight maneuvering and navigation, was work done with Ivo Ross as a graduate student and a postdoc, and YT Lin. Dave Williams, I'm not really going to talk about his work when he was a postdoc with me, and Partha was also a postdoc working on pigeon flight control. So this is, for those of you who haven't ever visited the Concord Field Station, this is an aerial view of the Concord Field Station. I'm located in this building down over here. We have a wind tunnel building up here, where we also have the X-ray video facility. And then we have an area where we can run animals over force plates here. So here's, back in the day, Craig McGowan was a graduate student running an emu over the force plate. And the emu adjusts to the New England winters quite well, and they're outside in the back. Our last emu unfortunately died at 23 years of age just this past fall. So this is a wind tunnel that we use for training birds to fly in the wind tunnel. I'll show you very few experimental measurements using the wind tunnel. Most of it's going to be on the birds flying through cluttered environments for looking at their navigational control. But we built this wind tunnel that allowed us to train. Here's Ty Hedrick when he was a graduate student flying cockatiels to fly in the working section, so we could look at aerodynamics and biomechanics of flight over a range of flight speeds. So the outline of the talk, again, is going to be starting off just generally about how we assess in vivo muscle function, comparing the methods for terrestrial locomotion with flight. Then I'm going to talk about how the in vivo muscle dynamics can help us understand the underlying stability responses of guinea fowl as the animal of choice that we study during running locomotion as they deal with breaking through the ground or obstacle perturbations. And we're going to sort of ask the question of what's the role of intrinsic muscle properties, force velocity and force length effects relative to proprioceptive reflexes. And then we'll switch over to the studies on flight, which is going to mainly focus the star animals, the pigeon, navigating through cluttered environments. They're really great animals for having them trained to fly between perches. Not so good in wind tunnels, so it's not going to have too much of an emphasis on wind tunnel flight because pigeons just don't fly well. But we'll finish up with how we think pigeons, what the visual guidance cues might be for guiding a pigeon flight through cluttered environments. So these are the traditional classic quasi-static muscle properties that we think of, we teach in our muscle physiology courses. the hill-type force-velocity relationship in blue. This would be the power output that could be generated over a range of shortening velocities. And so at very high shortening velocities, the muscles generate relatively low forces, but then as they shorten at lower speeds, they get to an isometric force. And then if they get stretched eccentrically, they can develop very high forces when they're actively stretched. The other classic property are the force length properties of muscles, the active force length curve and the passive force length curve, the active curve being determined by cross-bridge interactions between actin and myosin, and the overlap between actin and myosin in terms of the number of cross bridges that can be generated. And this was actually one of the fundamental measurements done to verify the sliding filament hypothesis for muscle force generation. And then this is the passive force muscles will develop when they are actively stretched in longer lengths. So the overall total curve would be something like this, where you'd add the passive force curve to the active curve. But these are quasi-static properties under very controlled contractile conditions. And when animals are moving around, such as these, the champion endurance. I'm going to pause the sound here so you don't have to hear the sound back. So these pronghorn antelope running around, so they're moving dynamically, running or flying. Animals have to worry about muscles turning on and off and undergoing time-varying changes of force and length under in vivo conditions. So we're interested in how these properties play into the in vivo dynamic changes in muscle force and length. And then how can these intrinsic properties of velocity effects on force generation or length effects on force generation interact with neural feedback control to control the animal when it is subjected to unexpected perturbations. So an example, because I'm not going to talk about them beyond this one slide, we started off measuring muscle tendon forces in wallabies when I was on a sabbatical many years ago in Australia. We used these E-shaped buccal transducers to put on the tendons of the animals. And there's a strain gauge here on the middle arm that gets deformed. And we can then calibrate that to force output of the muscle tendon units. And then these are the sonomicrometry crystals we usually use. For the wallaby, we'd use these larger 2 mm crystals. For smaller muscles, we use the 1 mm crystals that allow us to measure by propagating sound from one crystal to the other, allows us to measure directly the length changes of the muscle fascicles over time. And this is an example of the force measurements made in the muscle tendon units of the plantaris, gastrocnemius, and flexor digitorum of a wallaby while it's hopping on a treadmill, along with the EMG. And so we can take those sonomicrometry measurements, which measure length change relative to the force measurements measured from the tendon buckles, and relate the force and length measurements to when the muscle is being activated. So this is the pattern for the plantaris for a single stride during a hop. This is the gastrocnemius. And then if we plot the force versus the length over here on the right, we get an in vivo work loop. So it's a measure of the changing force relative to the length change of the muscle. And what you can see for the plantaris is that initially there's a little bit of shortening and then it gets stretched a little bit. And as the force is developing, it undergoes this little bit of stretch, but then it more or less is isometric or shortens just a little bit. So it has virtually an active spring-like force length relationship, but so it really doesn't do much work. It's more or less a controllable spring that the muscle is acting to generate force to very high levels connected to its tendon. The gastrocnemius does a bit more shortening while it's developing force here. So you see a little bit of a positive work portion at the onset of force development. But then again, it also is more or less isometric or changing very little as the force peaks. And so the net work during these large force developments are relatively small. So these are in vivo work loops of a terrestrial hopping animal. It's really designed for economical force generation, storing and recovering energy in its tendons, and not really doing much work with its muscles. Okay, so they're sort of an extreme case of muscle tendon architecture and function where the muscles really aren't doing the kind of work that we would normally expect a muscle to do, but they're actively control the forces that they can generate and transmit to their tendons. We also did experiments with wallabies hopping on an incline treadmill in a subsequent study where you might expect the muscles would have to shorten more and contribute more work to allow the animals to hop uphill, but that we found that the muscles didn't change their behavior when they did incline hopping, and it's really the proximal muscles around the hip and the knee joint that generated more work to increase the potential energy animals as they hop up an incline. So in contrast to the muscle tendon measurements we can make in running animals or hopping animals, and so Tom Roberts' group has also done this in turkeys with their tendons. In flight, there really aren't long tendons to which you can put tendon transducers on, at least none that anyone has yet been able to achieve. So we came up with a method to put a strain gauge, attach a strain gauge to the deltopectoral crest of the humerus. We originally did this in starlings, but we've mainly focused on pigeons, cockatiels, and doves. So this is this anterior process on the humerus of the bird's wing, and the pectoralis, the large ventral muscle down here, inserts onto the inferior surface of the deltopectoral crest. Not all birds have a really well-defined deltopectoral crest, so this method is really only allowed to be able to work where animals have a well-defined pectoral crest. And the strain gauge basically measures the deformation of the bone, acting sort of like a cantilever as the muscle pulls on it to pull the wing down. And we can calibrate the strain output of the strain gauge to applied force when we stimulate the muscle to contract or when we pull on it and do a pull calibration. And you can see we get a pretty faithful measurement of strain measured and the strain gauge mapped onto the force. So it effectively acts as an internal force transducer on the animal. So we can use those strain measurements and calibrate them to muscle force. And then similar to the wallabies, we use sonomicrometry to measure muscle fascicle length change and EMGs to measure the muscle's activation pattern. So the other advantage of birds is that in terms of understanding muscle function, in terms of whole body movement, is the pectoralis of birds generally, this is a single pectoralis, is in the range of 8 to 11% of the animal's body weight. So the two sides of the pectoralis comprise almost 20% of the animal's body weight. So that really measuring the performance of the muscle, the pectoralis muscle in a bird during flight, allows you to really gain insight in the overall mechanical requirements for flight. That's really difficult to do in a running animal where there are multiple muscles contributing to movement and control of joint motion in the limb. So this is an example. It's a bit of a dated video. I still like it. It's one that Ty Hedrick put together of a cockatiel flying in our wind tunnel with making these recordings of muscle force from the strain gauge on the pectoral crest and length change from the sonomicrometry crystals and then the EMG inactivated. And so what you're seeing is a dynamic changing muscle force versus strain pattern representing the in vivo work loop of the pectoralis cockatiel while it's flying at about, I think, 11 meters per second. And you can see that this is, in fact, a loop. It's an open counterclockwise loop. So this represents the amount of work that the muscle does over one contraction cycle. So the area within this loop is the force times length, or strain is the work that the muscle does each contraction cycle. And that's quite different than the pattern we saw with the wallabies, where they're much more isometric or these very stiff spring-like stretch extension contractions. So we can take the in vivo measurements of the muscle and the work output of the muscle, and if we multiply that times the frequency of the muscle contraction, we can actually measure muscle power output. And so we've done that for 3 different species of birds flying in the wind tunnel. We originally did it with magpies. We weren't using sonomicrometry, so we were estimating muscle length changes from kinematics. But in the cockatiels and the doves, we were able to then measure the power output of the muscle at different flight speeds. So the wind tunnel allows us to train the birds to fly at different flight speeds, from the lowest speed that they'll maintain up to the fastest speed. And this really represented the first sets of direct measurements of muscle mechanical power output in flight. Up to this point, the field of flight aerodynamics really rested on quasi-steady aerodynamic theory, which predicted U-shaped power curves. So that's a lot of power has to be expended, induced power, when a bird hovers. That's why hovering is hard. Hummingbirds do a good job of it, insects do a good job of it, but most birds really have to struggle to fly at very low velocities close to hovering, and they're really non-sustainable flight for these birds. And then there's a minimum power curve, which drops off and then increases again as the parasite and profile powers increase as the birds fly faster due to the drag on the wings and the body, even though the induced power is falling off, so you get a U-shaped power curve. So we were able to show in these studies that I think it's unclear what the magpies are doing. We suspect that maybe they were limited in how fast they could fly. It was a smaller wind tunnel that Ken Dial had in Missoula, but clearly with the cockatiels and doves, we see this U-shaped power curve. So it sort of shows that even though there's unsteady aerodynamics going on, the overall power requirements for flight show this U-shaped power curve. So that sort of gives you a sense of the in vivo measurements we can make during flight or during terrestrial locomotion. So I'm going to now focus on our measurements relative to how these measurements can be used to study the stability of locomotion. And I'll just summarize that going back to the force velocity curve, we think that muscles operate in different regions of the force velocity curve. If they're operating here where they're shortening at higher velocities, not generate as much force, but they are doing a lot of work to produce positive power output that's necessary for flight or swimming or cycling or jumping. Intermediate, where the velocities are very low, they get isometric forces, which are reasonably high, where muscles are acting more like to be a strut-like, controlling the position of a joint. And then muscles that undergo either energy absorption under a negative work loop, they can absorb energy very effectively, so they can act very effectively as dampers, or if they go through a stretch shorten cycle, they can produce very high forces economically. All right, so the work on the muscle dynamics underlying stability was largely work undertaken by Monica Daly when she was a graduate student with me here. And I've been blessed with some really stellar graduate students over my time. So here's a video of the guinea fowl running down a runway that it thinks is solid ground along the whole length. This is tissue paper, and it's going to break through and hit the force plate. So I'll just show you this video. So this is from a while ago. These are papers we published in the early 2000s, 2007 through 2011. And the bird basically is able to run and break through and stabilize. And we are interested in understanding center mass dynamics of how they control potential and kinetic energy of their center mass, as well as the underlying neuromuscular and muscle contractile dynamics. And so she had identified two important critical conditions that determined the stability method strategy that the bird wouldn't consciously make, but what would result in the way it would stabilize was the relative limb angle at contact and the limb extension at contact. So these were obviously a variable patterns. The birds don't break through and show just the sort of stereotypic running behavior that they would if they're running on solid ground. So there was variation in the patterns that emerged from when they had to stabilize after breaking through. But this is about a 40% drop in their hip height. So you can get a sense of this is a fairly substantial perturbation of the animal to have to stabilize, dropping potentially as much as 40% of his hip height. So this just as a comparison to show you a bird dealing with a visible step. So vision in this case doesn't help. We'll see later during flight that vision obviously is a very important cue for the birds to navigate. But in here, it suggests that if any kind of central processing of visual cues doesn't really help the bird, they stumble and slow down quite a bit when they actually can perceive the unnatural obstacle that they have to run over. So we came up with three hypotheses of how a guinea fowl might stabilize their center of mass mechanics using this mass spring model. So the first would be the animal would extend its leg fully into the ground so that the center of mass trajectory of the dropping potential energy and variation with kinetic energy would be the same as it was when it's running on level ground. So there'd be no change in center of mass energy state. The other is that the animal is falling into a hole, and so what it's doing is it's losing potential energy, but it could stabilize by converting that potential energy of its center of mass into mainly forward kinetic energy, but also vertical kinetic energy. So it stabilizes by speeding up the range, its overall range of motion. The third case would be that it falls in a hole, and so what it does is simply absorb all that energy using its muscles, which are very effective then as dampers to be stretched, undergo eccentric contractions, and absorb that energy as it goes. And so the potential energy gets converted to energy absorption. And without going through all the background of that, what we found was never did the animals extend fully to maintain no change in center of mass energy state. About 2/3 of the time, they basically stabilized by speeding up, gaining kinetic energy as the potential energy fell. And then about another third of the time that they would absorb the energy. And those initial conditions determine whether energy absorption mode was more likely to occur than. So if they had a lower point of limb contact angle, they would absorb the energy, whereas if there's a more vertical limb orientation, they would tend to speed up to stabilize. But they were very robust in being able to deal with this substrate height drop. But these were hard experiments to do. You've got to have the animals run back and forth. The experimental limb doesn't always land in the hole where you want it to. So we actually moved to a different approach. And I just want to point out that this was work that was very much inspired or stimulated by Devin Ginrich's work with Bob Full when he was a graduate student with cockroaches running along and having a little cannon perturb them while they're running along and looking at intrinsic mechanics that stabilize them within a few strides as the cockroach was. This is obviously very much a slowed down video, but this is the cockroach running over I imagine it might have been a forced platform, but the cannon explodes, provides an impulsive perturbation, and the cockroach is able to stabilize. So um, we were not the first, but several groups have been arguing for the importance of immediate intrinsic properties of force length and force velocity effects acting as preflexes before the nervous system can even react to stabilize the animal. So just to give you a sense of the muscle dynamics of the bird while it's now running over this force platform when it breaks through the tissue paper. So we're now looking at the way in which the muscles, the lateral gastrocnemius is going to function during this breakthrough perturbation. So we're using the same methods we used with the wallabies, where we have these tendon buckles measuring length, muscle tendon forces, sonomicrometry for length change here, and EMG. And so above, this is the control pattern of the lateral gastrocnemius while the bird's running on level ground. So it undergoes a bit of shortening. And here's the force development following this is a rectified EMG showing the development of force after it's been activated by the nervous system. And what you're going to see is, as it runs through, you're going to see the breakthrough stride played out as a video on top of this control stride. And so what you can see is the limb extends much more to deal with the drop in height. The animal's 40% of its hip height. And so it shortens more. It also shortens at a higher velocity. And not being able to make solid contact with the ground, what happens is the force just doesn't develop nearly as effectively. You can see the effects of reflexes later in a later stride here as it's trying to regain control of itself. But there's basically, it has a feed forward anticipatory activation of the muscle. There's no resistance. It's shortening more quickly. And as a result, the force falls off well below what it would during steady running. So those experiments were hard to do. And so what we actually did, most of the work we did subsequently was on using obstacles on a treadmill. And so instead of falling through a hole, we're now looking at animals having to deal with overcoming obstacles in their path. So these are like 5-centimeter obstacles shown right here. And they're covered with black neoprene, the same sort of thing that you make a wetsuit from to sort of prevent the birds, to minimize the visual cues that the bird would have. So over here on the left shows the obstacle that's going to come around on the treadmill. We always use a mirror to encourage the birds they're social animals. They like to be around each other. So we find mirrors in the front of the treadmill helps engage them to stay running in the front of the treadmill. So I'll play the video to show you now the same recordings. Now, this is the control level running of the guinea fowl. Here's the EMG and the muscle pattern of the force development during controlled locomotion. So again, the muscle is generally isometric, a little bit of shortening, so it does a little bit of positive work. Very similar to what we saw with the wallaby when it was hopping on the treadmill. It's a relatively isometric contraction, a little bit of shortening, so it does positive work towards the end of the stride. But now it's going to have to climb up over the obstacle to stabilize. So we're going to play that video pattern compared to the level running pattern. And so what you can see, and this will loop through, is the bird has to flex the limb at the ankle and the knee, presumably as well. But to rise up over the obstacle, the ankle remains in a more flexed position. That means that the muscle operates at a longer length, and it develops much greater force than it does, and an earlier force development than it does during steady level running. So there's an immediate length effect and velocity effect, lower shortening velocity effect, that allows the muscle to develop greater force. And then there's also evidence even though we don't show it too clearly in this EMG here, of reflex feedback that subsequently comes into play. So we think that the preflexes, the intrinsic properties of the muscles, provide an immediate stabilizing effect that then allows the time for the proprioceptive reflexes to recruit additional muscle fibers to generate greater forces. So again, overall, a very robust response to being able to stabilize the animal while it's moving over an obstacle. So now this is what we would consider, what I'm going to show you now is the most recent set of experiments we've been doing with guinea fowl. This is what the so-called intact lateral gastrocnemius studies. This is when the bird has all of its proprioceptive reflexes intact, right? It's just a normal bird, except that we've got a force buckle in its tendon, EMG electrodes, and it's also got the sonar micrometry crystals. So we asked the question, well, what is the role of proprioceptive reflexes if these intrinsic properties look like they're really providing a good stabilization? To what extent is the nervous system important? And the two main proprioceptive reflexes are the 1A spindle afferents, the so-called stretch receptors, and the 1B Golgi tendon organ force receptors. So these are, again, proprioceptive reflexes that we traditionally talk about when we're teaching a muscle physiology class. And these are classic diagrams, one from my book, of these 1A afferent reflexes. It's the only monosynaptic pathway reflex to the motor system. So the spindle organ gets stretched. It sends an action potential up through the dorsal root ganglia and down through, and then in synapses on the ventral motor neuron population that goes back to that same muscle. So it's a single monosynaptic stretch reflex. This is what the doctors, when you go in and test your 1A receptor reflex, they'll tap you on your patellar tendon, stretching the spindles in your quadriceps muscle. It sends up and then it stimulates, activates the motor neurons to that muscle to be activated and contract. And there is corresponding reciprocal inhibition to the opposing flexor muscles of the same limb. And there's also appropriate stimulation or opposing inhibition across to the contralateral limb. So reciprocal inhibition is mediated through this stretch reflex, as well as the control of enhanced activation of the muscle that's being stretched. So it turns out that when you cut the nerve to a muscle and you allow it to grow back, it's called a reinnervation protocol. The motor innervation to the muscle grows back. So here's the motor innervation coming down and innervating the muscle fibers to contract and generate force. Those of us from biomechanics think about this and that muscle force generation. But the sensory afferents don't grow back. Or if they grow back, they lose their synaptic efficacy here within the spinal cord. So there's no 1A return to the muscle when you do a peripheral nerve reinnervation experiment. And this came about from people wanting to study how nerves would recover following injury. And there are a series of studies by Cope et al. And Abelo et al. At Emory that showed that in cats, if you cut the distal peripheral nerve, you would lose the 1A monosynaptic reflex, the sensory afferents, the primary afferents to the muscle would get lost, but the motor neurons would recover and repopulate and innervate the muscle. So you'd recover motor activation and EMG. So we explored whether this would also be the case for guinea fowl, and it was. So we just set up an experiment where we cut the peripheral nerve to the lateral gastrocnemius of one limb, let it regain its motor innervation after about 4 to 6 weeks. It takes about 4 to 6 weeks. And then we did the opposite side limb. So they were bilaterally underwent reinnervation and proprioceptive deficits to both the left and right LG muscles. And then we did our experiments, putting a tendon buckle on EMG and sonar micrometry crystals to measure the dynamics of the muscle while the bird is running with this proprioceptive, the lack of its 1A afferents feedback. So this is a guinea fowl running at 13 weeks of age, and it sure looks like it's doing a good job. You wouldn't know from this video that it had lost any, had any proprioceptive deficits to, primary ankle extensor muscle. But we wanted to actually compare what this reinnervated LG, how it compares to that of the intact LG. So we compared our results for the reinnervated LG to our earlier measurements on the intact LG, and we published those results in eLife a few years back. So this is a complicated panel, but it basically shows you the way in which we structured these experiments was we analyzed the stride before the obstacle, the stride going over the obstacle is SO, the stride after the obstacle, and then the second stride after the obstacle. And what you're looking at in the upper panel are the data we originally got from the intact LG muscle of the guinea fowl. I think it's 5 animals for each group. And then below are the new animals that went through the bilateral reinnervation. And it shows the patterns of the animals with the proprioceptive deficits, the length change pattern under these different stride conditions, the muscle tendon forces under these conditions, and the EMG. And I hope what you can see is generally what I labeled here at the title of the slide is that really they're very similar patterns between the intact animals and the reinnervated animals. So the loss of proprioceptive feedback, that deficit, doesn't seem to drastically influence the muscle tendon force dynamics. There are changes in EMG, which I'll touch on in a second. But overall, the overall mechanical properties of the muscle, its in vivo ability to generate force and undergo length change, shows very similar patterns for the animals going over the obstacle stride versus level terrain. So the light black lines here and here are just control running over level terrain, and the orange lines are the reinnervated muscle pattern, and the blue lines traces are for the intact LG when it had its reflexes intact. So overall, there's very similar force length dynamics in EMG for the two groups of animals. And if we then look at the in vivo work loops of these two groups of animals, the muscles during these 4 strides, the one preceding the obstacle, the one on the obstacle, and the 2 after, we again see qualitatively very similar work loop patterns where the muscle does additional work by generating a higher force, mainly by generating more force over the obstacle stride. That was even more strongly seen in the reinnervated muscle than in the intact muscle. And this stride after the second one after is more or less what we would consider equivalent to the level control running, and you can see it matches pretty well what we'd observe when the animal's running on the level, on a level treadmill, and that's the black line again would be the level control running versus the 3 strides when it's having to negotiate over the obstacle. So for at least for fast running, fast locomotion, the intrinsic force length properties help to explain a large fraction of the force generation of the muscle of the LG and its work modulation to control for the ability of the animal to rise up over the obstacle, generate additional work and force to be able to elevate its body and move over the obstacle effectively. So there are some subtle differences in the EMG patterns. We found that basically for the reinnervated LG, the animals developed an anticipatory activation of the muscle, so it came on more earlier than the intact LG. So we interpret that as a stronger feed forward gain on the muscle. And down here, you can see the phase shift here was significantly advanced on the obstacle stride, as well as the stride preceding for the reinnervated LG muscles compared to the intact muscles. So the birds compensate to some extent by activating the muscle earlier in the stride cycle when they've lost their proprioceptive deficit or feedback. They've lost the feedback and have a deficit. And if you look at the EMG over time, we see in an obstacle stride that there is a compensatory reflex that follows the initial preflexive increase in force as it's running over the obstacle. So there's evidence of feedback here, whereas the reflex of feedback is lost in the reinnervated animal because they lack the receptor input from the spindle organs. But overall, really quite remarkably similar patterns for the reinnervated animals with a proprioceptive deficit. So that's what I just said. We ended up with, this is our overall summary slide in the paper, which showed that there's increased feed forward drive when the muscles have lost proprioception and they have that deficit. There's an earlier EMG activation, which I just showed you. There was also a slight increase in stride frequency. It's likely muscles from other muscles can have reflexive input to the muscle that's lost their 1A afferents. So other ankle extensor agonists in particular could also, their stretch reflexors would synapse on motor neurons to that muscle. So it's likely that variation in those heterogenic reflexes could explain some of the varying patterns we had across different individuals. There was an increase in the EMG frequency content of the activated reinnervated muscle, and as a result, increased force development, the rate of force development because of that. So there are differences, but overall, strikingly similar patterns that shows that the intrinsic properties of the muscle, force length and force velocity, provide for a lot of intrinsic stabilization. So I'm going to pause here and take any questions and check the time to see where we are. Okay, good. We're about halfway through. So does anybody have any questions on this part of the talk? Yeah.
I have a quick question. I'm sorry if I missed this, but did you remove proprioception from both sides, like
Yeah.
both limbs?
Yeah, we did bilateral. So it was a very complicated experiment. So you get the guinea fowl Keats as young animals, a few days of age, they get shipped to you, and then we reared them up, and we did the first set of reinnervation. You basically go in and sever the nerve and glue it back together, and it regains over a 4 to 6 week period. So we did those surgeries, the initial surgeries at 4 weeks of age on one side, and by about 8 to 10 weeks, they had regained motor innervation. We did EMG recordings of the muscle to see that its motor activation had come back.
Mhm.
And then we did the surgeries on the other side at like 8 weeks of age. And then we had to wait till 12 to 13 weeks of age for both muscles to regain their motor function. And then we could do the experiment to say, okay, well, how does the running biomechanics and the dynamics of the neuromuscular function compare to the intact muscles when they're intact? So we
So,
did,
so yeah.
yeah.
So I have two questions then to follow up on that. Is have you ever done it for just one limb and seen what happened?
No, we wanted to, well, I think they would probably I don't think, we didn't do it. We wanted to make as much of a impact on the animal's running ability to really have an effect. And
Right.
we were hoping to knock out the medial gastrocnemius as well. But turns out that birds, that's one thing downside of birds. Guinea fowl are great because they run really well. They're big. You can get access to muscles and tendons really well. But it turns out that the innervation to the MG is a separate nerve that also innervates all the flexors of the digital flexors. So when we cut the muscle, the nerve to the MG, it also knocked out all the digital flexors, and they would just go, they became lame. The limbs would just curl right up, and they wouldn't recover good locomotor capability. So we basically had to scratch the MG as an agonist. So these birds do have an MG, which is an important functional agonist to the LG.
Right. And have you ever done it in older birds, or can you do it in older birds and
I
see what
suspect you
happens there?
could. No, we haven't done it. They're hard experiments to do,
Yeah.
and it takes several, weeks or several months to do the experiment, and it takes a lot of time to do the surgeries and then do the
Sure.
analysis. So I'd say that the one thing that we did do is we compared the animals while they were walking, innervated, versus reinnervated versus intact.
Mhm.
And so Janneke Schwaner, who was a postdoc with Monica, finally analyzed those data, and those just got published in JEB this past year. So
Mhm.
I'm happy to talk about them outside of this, presentation, but they're really hard experiments to do, and
Yeah.
it takes a lot of effort to do them and then go through the data analysis. So, I mean, those are good questions. At what point does age become a problem in terms of
Exactly.
recovery? Yeah,
Yeah. Yeah. Thanks.
I don't know if there's any. I can't really see whether there's anybody asking questions. So I guess people just have to pop up if they want to. All right. Well, I'll go on. All right, we're going to switch gears. We're going to go to flight, and it's going to be more flight navigation.
The master of maneuverability,
So this is a
solving
goshawk.
the ultimate challenge, flying through woodland.
So I'll let this play for a second.
It feels for the air like an eagle, swings its wings like a falcon, and all the time just inches from the ground and a breath away from collision with a tree. Split second.
All right, so that was our video that we always would show to when we were collaborating. Was a ONR Muri grant with a bunch of engineers interested in controlling UAVs and birds, obviously. And if you go on YouTube, you can find now lots of videos of birds showing remarkable abilities to maneuver through tight spaces, small openings. So that was an earlier one that the BBC did they had falcons flying at high speeds, but this was the goshawk navigating through cluttered environments. So the question was, what are birds looking at? What visual cues are they using to guide them as they fly through these really cluttered environments? And that's what the goal of the work was. So as you're driving down a road like this and you've got the trees moving by you, there's optic flow that you see. Now, birds have the goshawk or an eagle, birds of prey have binocular visions. They have front pointing eyes, so they have a certain part of their visual field is binocular. The birds we studied were pigeons, which largely are monocular. So either eye is looking out, has a monocular field. There's very little, their binocular overlap is just for their short-range vision for pecking at feet, you know, feed or seeds that are on the ground in front of them. So, but either monocularly or binocularly, you're going to end up with this optic flow, which is the angular velocity of motion, and the looming. So objects increase in size and increase in their angular velocity as they approach. So it's important to be able to understand what those patterns of motions are, because it provides a sense of things that are moving in their environment towards them, or in the case of navigating through the environment as you're flying through or running through a complicated environment, it provides cues about your self-motion relative to obstacles that are fixed in the environment. So it really gives you a good cue as to your self-motion and the direction that one might choose to move relative to obstacles that are in your way. And so animals have to sense both of these, the objects that are moving towards them, potentially a predator, or objects that are fixed in place, but due to the animal's own self-motion, induces these optic flow cues. So just to point out, because I'm going to come back to it, in the middle of this is the focus of expansion, and so at the center is where this optic flow field will, right at the center, there's no motion. So it goes to zero right at this focus of expansion. So at a long distance, right in the center of the field, the angular velocities and size go to zero. So we have this cluttered environment. We saw the goshawk flying through the forest, these trees. There's a lovely trail through the woods. Obviously, as long as you stay on the trail, you don't have to worry about encountering obstacles. So the problem was, how do we make an obstacle course that we have to fly birds through? Well, we came up with, again, the traditional experimental approach was to come up with an artificial forest. So on the left, you see a pigeon flying through a vertical forest of PVC poles, 15 of them. And so this was our virtual forest over on the left here. And it measured 3 meters by 3 meters. And we trained the pigeons to fly down a corridor. This isn't quite to scale, about a 10-meter long length before they approach the obstacle field, and then another 7 meters to a target perch. So we trained the pigeons to fly from a starting perch to a target perch with no obstacles. And then we started introducing obstacles. And I didn't think of pigeons as navigating cluttered environments. They're usually open space, cliff-dwelling animals. You know, you find them roosting on ledges of windows in buildings. So I thought when we put up this array of poles, we may have the pigeons just turn around and say, forget it, I'm going to just fly up and turn around and go back to the starting perch, and not if you're going to put poles up in front of me, I'm not going to fly. But in fact, they actually all flew through in a fairly directed way. They had to navigate through these poles, and we randomized the distributions of these poles in terms of their location. So there wasn't a fixed position, and the birds would then have to encounter a new distribution of poles. We have little reflective markers here on the poles so we could measure their positions from a camera array, as well as we have markers on the pigeon's head and body so we could measure the direction of the pigeon's flight path and its head orientation while it's flying. And we were interested in looking at a series of visual cues, the looming cues, the size of the poles, a parameter called tau, which I'll come to, about time to collision. It's where the bird might be flying directly into a pole and colliding with it, or the angular position and velocity of a pole relative to the bird's flight paths, which again is things that are going to change due to the optic flow that the bird is navigating through. And again, this was work funded from an ONR grant collaboratively with engineers that were interested in guiding UAVs. And Evo and YT were the two main principals helping me with this project, and they carried out most of the experiments. So what you're seeing now is a head camera on a pigeon. It's just a cool video. That's Evo, and YT's at the end, and you get a sense of what it's like to be on the head of a pigeon flying through this. Okay, and I'll let it play one more time. I've always loved this video. It was actually done in 2010. So that was our initial corridor we set up. The birds could fly down. That's where the experimental runway is as well. So this is the bird going through saccades on the perch. And then it flies. And you can see there's distortion from the camera. It's not the greatest video image quality, but it gives you a good sense of what it's like to be a bird flying around and flying through the space. So we did a whole series of these tests of pigeons flying through these randomized pole distributions. And in the green are the paths the pigeons took from the starting perch to the landing perch flight paths, which are generally linear and straight. and they don't vary too much. There's a little bit of variability. The pigeon starts off a little bit to the right or the left, but they're mainly straight. And you can see the average, the mean, and standard deviation of the flight paths when it's unobstructed versus when we had obstacles, these 15 poles in place. And you can see the flight paths are much more tortuous. They have to navigate around the poles to get to the landing perch. But you can see the average direction of flight path of the pigeon is basically straight. It's a goal-oriented flight behavior. It's trying to fly from a takeoff perch to a landing perch. And overall, it does that. It just has to take a much wider range of motion to navigate around the poles. And you see that from the point of view of both, it has a longer distance to travel versus the straight line path. If it was to fly perfectly straight, it would be 1. So there's a little bit of non-linearity in the flights unobstructed. But for the most part, they're pretty damn straight. And here the bird's having to navigate back and forth. So there's a change in bearing of, on average, 87%. There was the bearing changes in orientation. That's the flight direction. We're up to 60 degrees of the flight path. The birds had to slow down. They flew slower when they're having to fly through the obstacles, not surprisingly. They had to navigate, and that took them to do that without colliding with obstacles. They had to slow down. So they slowed down by almost 50%. And then they also had to increase their wing beat frequency. So this navigation came as a cost to them. So presumably a higher metabolic cost or power requirement to fly with a higher wing beat frequency, to accelerate and decelerate as they're maneuvering through the obstacle field. So it was, definitely a more demanding flight. But fortunately for us, they did it. So we were able to look at them flying through. And importantly, we noticed two characteristic aspects to the flight behavior. Was that we didn't notice any sign of steering until about 1.5 meters before the obstacle field, which is this gray area here. So we use 1.5 meters as the distance of what they're paying attention to, something in front of them as being important. And we also use 60 degrees as the range of things they're paying attention to. So they're heading in a certain direction. We assume they're now paying attention to things that are 30 degrees in one direction and plus or minus 30 degrees from their heading direction. So overall 60 degrees. So we define this as an attention zone. And so this is, and so what we were interested in is saying, well, what are the potential cues that they might be using, giving these flight paths? So here's an example flight through the obstacle field, the bird's flight trajectory. And we could calculate the angular size of all these obstacles for each individual obstacle. Each one has a different color. As they fly by, the angular size gets large and then it gets small again. The angular position grows very steeply as they go by it. And then once they go past, we stop the plot. And then the time to collision, tau, which is the looming, the size of the obstacle divided by the loom rate. And that might maybe be obscured. I mean, on my screen, it's obscured because I'm looking at you listening to me as an audience. But when tau goes to 0, when the loom rate gets really, really large relative to the size of the obstacle, that means you're basically colliding with it. So it's a measure of time to collision. And there's a really cool classic paper David Lee published in Reddish in Nature in 1981, using tau as a cue for time to collision. So these are gannets that are feeding on fish in open water. And he worked out that they can use time to collision, or tau, a visual cue, to determine when they should retract their wings before they contact the water. Otherwise, the huge drag force on the wings could break their wings. So I'm going to play this video for you. Presumably some of you haven't seen it.
Once they've selected their target, they plunge from heights of 30 meters, striking the water at 100 kilometers per hour.
So you can see how they retract the wings just right before they make contact with the water.
Every dive subjects them to enormous forces.
They're like these little darts or spears getting the fish underwater. Pretty impressive. So this was clearly an important visual cue that they use for knowing when they should retract the wings before they hit the water. Well, we thought of that. We looked at tau, but we also thought angular position might be important. So we hypothesized, rather than the birds avoiding the obstacles, we thought they maybe would be targeting the gaps between obstacles to determine their flight trajectory. So we focus on angular positions because tau turned out not to be a really good predictor of their flight paths. So we started looking at where would be the based on angular position, where would be the widest gap to which they would want to fly, and making choices to fly around obstacles based on the widest gap within their attention zone. So this followed from the studies that Partha did with Srinivasan of budgerigars with flying down the corridors. So these are little parakeets flying down corridors with different gratings on either side of the wall. So the gratings that are vertical have a much higher optical flow, angular velocity rate, versus the ones that are parallel. The parallel walls induce a much lower optic angular flow. And notice that the birds are biased towards the walls that have the horizontal obstacles versus the vertical obstacles. And then when they're symmetric on either side, they fly right down the middle. So this was evidence that they use optic flow, the rate of angular flow of their visual fields on the left and right sides, to balance optic flow to choose a flight path. And so that really matched with the idea of choosing a gap in which the optic flow of the left versus right obstacle of that gap would be relatively balanced. This is the closest thing to math that I've got for you. So this is a proportional differential controller that we YT developed to model the flight path steering and guidance of the pigeons navigating through our obstacle field. So it's got a proportional gain and a derivative gain. It's got a delay. It's got inertia, and these are fed through the sensory perception feedback to control how that bird then chooses to affect based on the attention zone. Works through the attention zone to decide which gap it should aim to. So here's a bird flying along at this instant in time. We decide that these are the obstacles it's going to pay attention to within the attention zone. It's not going to pay attention to that one or that one. It's only paying attention to these near ones that are within 1.5 meters distance, and it's a plus or minus 30 degrees from its current heading. And that determines the steering direction based on the proportional and derivative gains and the delays inherent in this. And we used a continuous steering model that was updated every 100 hertz, which matches the flicker fusion rate of the pigeons, what the sort of the frequency at which light won't flicker. If you have light flickering back off and on, you have to go up to over 116 flashes a second before the pigeon thinks the light's continuously on. Obviously, much lower flicker fusion rate for us, around 30 hertz, to think that the light is steady if it's being turned on off and on at 30 times a second. So based on any given point in time, the pigeon makes judgments about what it should be choosing to go based on the angular velocities guiding its flight past these obstacles. And it's always going to choose an opening between any two obstacles in the line of its vision and to make a decision whether it flies here, or does it make a turn to the right or turn to the left. Okay, so it detects the obstacles, it makes a steering decision based on these proportional derivative gain controllers, and then chooses the flight path as a result. And he did basically as a whole tuning thing of working out what the gains should be, and worked out what they would be. So I'm not going to go through that. It's in the paper. And we tested 2 different models. This is the gap aiming model that we were focused on, and an earlier model that really was developed more for how people navigate through cluttered environments, such as when you're walking down a sidewalk or in a filled room, and how do you avoid running into somebody or walking into somebody. So Warren and Fajan were using obstacle repellence model. We used a gap aiming model. And then it was important to include some sensory uncertainty. The birds can't see perfectly. There's jitter and delays in the response time. So we included some degree of sensory uncertainty in the model. And so what we looked at was the predictive power for being able to navigate through these obstacle fields, given different levels of sensory uncertainty. And what we found was that the predictive power had a maximum and a minimum, but the mean value was here, and it was basically largest for the largest visual gap rule rather than being guided. So we had 3 different gap aiming rules: a destination gap, which would be where the target landing perch was; a flight direction gap, which is the current heading of the bird, choosing to fly in its current direction, irrespective where the obstacles are, or where it actually steers towards the widest gap. And you can see that the steering towards the widest gap gives the greatest performance in terms of the predictive power and the ability to react to obstacles at a given distance, less than a meter away. We got much higher predictive powers for the gap aiming models rather than where we where the birds or the model reacted to obstacles that were within half a meter away, and less so when the birds were either lower obstacles or obstacles much further away. And so if you look at a series of the measured flight paths that the birds took, that's shown in red. Those are the experimental trials where we could take the bird's XY flight path relative to the obstacles versus the model trajectories. We got 70% of the flight paths were steered accurately using this relatively simple left-right optic flow model. And it was relatively simple and easy to implement. And if we did an independent simulation, 120 free simulations, YT found that the model would fly through the obstacles randomized over time through all the simulations with 90% not involving a collision. So it was very robust in terms of avoiding collision avoidance. So whether anybody ever implemented that flight simulator in the UAVs, I can't really say, but I do know that I'm going to let this play.
Fast, accurate, and repeatable flight.
So this is our collaborators at MIT,
Capture for feedback control.
inspired by our birds flying through poles.
That is smaller than the aircraft.
So they had two poles.
Accurate control.
They had a UAV with wings,
because of the complex
and they
airflow
were able to
induced
use
by
their
a
controller
flight
to be able to navigate by
path.
rolling.
120 frame per second onboard video.
So they used a
for
onboard
study
video to control the flight path of the. So that's
Here,
what the
we
engineers were
demonstrate
able to
avoiding
achieve compared to what our
vertical
pigeons
and
were able to achieve.
horizontal obstacles.
So I would say they still had some work to do. All right, so I'm going to finish up with what do birds actually look at when they're playing? Because this is kind of this is work we actually haven't yet published. It's been a while trying to get Evo to finish up the analysis, but we're interested in what are the visual cues that birds use in the directions of flight that they move. So we basically built this structure on top of the head where the bird, it's got a camera on its head with some mirrors. So we're going to try to map out the direction of where the eyes are looking relative to the head's motion. And this came out of work that Evo did with pigeons when they make these 90-degree turns while they're flying. You should be able to see that the head undergoes these horizontal saccades. So there's that's a rapid motion of the head to then gaze stabilize in the new position of the head. Because we had the hypothesis that birds follow their head when they're turning, and the eyes remain fixed relative to the head. And that video has a terrible audio. So most of you can think of pigeons moving around, undergoing these head saccades when they're walking on the ground. It's a thrust and hold phase. So there's a thrust phase for parallax motion detection, but then a hold phase for them to be able to gaze stabilize and look at things that are moving relative to them. So in the case of flight, nobody described saccades of the bird's head while it's flying, but we actually observed that in pigeons. So we came up with this pretty crazy experimental design where we mounted a camera, balsa wood platform with mirrors that would image either left and right eye of the pigeon. Okay, so the camera is viewing the reflection of the eyes off of either mirror. And I'll show you the videos that we get from that. So this is Evo releasing the pigeon outdoors at the field station. It's flying along, and then it's going to make a left-hand turn around and lands in a tree. We had to worry about hawks, red-tailed hawks in the area trying to take our pigeons down. So we got data for 3 pigeons with these head-mounted cameras and mirrors. And I'll just let this play one more time. Before he released the pigeon, he actually did a 360 rotation with the pigeon handheld. So now what I'm going to do is show you the video of the eyes. It's less exciting than it might sound. So now here's the camera. Now he's rotating around 360 degrees, and you see the bird's eyes going through these saccades, trying to gaze stabilize as he's rotating around 360 degrees. And then he's going to eventually release the pigeon in a little bit. And the pigeon's going to start flying. And you're going to see the eye motion when the pigeon starts flying. So he's holding it still. And there's just an occasional saccade every once in a while. Now he's going to release it just about now. So now the pigeon is starting to fly. And you can see how steady the eyes are while the bird's flying. So all we've got basically background motion of the bird. It's in the field of view of the cameras, but it's basically focused on the eyes themselves. So we've had to work out the motion analysis of the eyes from this video camera. So that's the bird then landing. So we're back to the beginning where he rotates the bird at 360 degrees. So these are really cool experiments. So we had a IMU on the bird's head that measured the head orientation in roll, pitch, and yaw. So this is when he rotated the bird 360 degrees, a yaw rotation. Virtually no roll or pitch. The bird's not being rolled or pitched. This is where he's holding it stationary. That's the second phase, right through here. And then this is the flight phase. Oops, this is the flight phase. And then you can see the bird then gradually makes a turn, a yaw back in the opposite direction as it flies around. So this is where the bird is flying. And down below are the left and eye movements in two different axes, a dorsal temporal axis, sorry, I'm going to use my mouse, dorsiventral axis and a nasotemporal axis. And you can see that when he rotates the bird 360 degrees, there are opposing saccades of the left eye, these quick, flat, rapid motions of the eye, the angular motions of the eye to help to try to stabilize the gaze of the left eye and the right eye. Then he's holding the pigeon steady. And there are these periodic saccades, sort of what you saw when the pigeon was flying in our corridor with it sitting on the perch. It goes through these saccades. You see pigeons move their heads rapidly every once in a while, or the eyes move. But at the onset of flight, this is 0, you can see that the eyes take on this flight position. They adopt a fixed position, so they really become very stationary relative to the head. So they assume a certain angular position in the dorsiventral and nasotemporal axis relative to the head. And this is important because it means then we can track head motion to interpret what's the orientation of eye gaze position while the birds are flying without actually having to map where the eyes are looking. And one of the other cool, so this just shows you a comparison of the range of motion of the eyes. Non-flight is in black versus during flight is the blue. So there is motion, but not much. I mean, we probably have a little bit of motion due to motion artifact, but it generally remains relatively fixed during flight relative to non-flight. And one of the cool outcomes we didn't expect was that the size of the pupil, because we can measure the size of the pupil from these measurements, increases by about 50% during flight. So we think there's a compensatory increase in the retinal luminance, so it gives a visual gain to the bird while it's flying. So these are experiments I keep hoping that we will publish, but this provides a working hypothesis for us that when the birds are trying to control their flight path, if they're heading in this direction, this is the gaze direct, this is the way they're looking, but they're moving in this direction. So the bearing direction is direction of the flight path. So if they turn their head and look this way, there's a gaze offset. Here is represented by about 30 degrees. That gives them a sensory cue as to they're moving in this direction because that's the center of focus of expansion of the optic flow cues. But if they turn their head, they can get a mismatch in that, and that gives them feedback control to tell them they actually have to turn their body by using their wings to rotate their body by 30 degrees. So we think that birds will, in terms of navigating complex environments, they steer towards widest gaps to avoid vertical poles rather than avoiding obstacles per se. And we think they stabilize their gaze in response to optic flow cues. And we've also done this for hummingbirds. I didn't have time to show you those experiments, but I think the experiments mapping the eye motion relative to the head gives evidence that at least pigeons we can demonstrate keep their eyes in a relatively fixed flight position with respect to the head. So controlling head motion is really important in where the center of gaze is relative to the center of expansion and that head side slip that can provide guidance for where they fly. So with that, I'll finish. And that's the CFS gang, many from Stacy Combs' lab at the time, back in 2017, so now 7 years ago, all a little bit older. So I'll finish there, and I guess I'll stop sharing my screen. Stop.
Thanks so much, Andy. That was a really fascinating talk. Does anyone have any questions?
I have a question.
Okay, yeah.
All right, I'll go. Do we know much about, I'm the fish guy here, I guess, so I feel like I should know this, but do we know much about eye movements in fish as they swim and undulate?
I don't know about eye movement. I know mammals, like primates in particular, like us, have tremendous, control of eye movements relative to the head. So you can shake your head back and forth and keep your eye motion. So that's optokinetic control of, or optical nystagmus, where the eyes remain fixed relative to head motions. I suspect fish. Boy, I don't know. That's a good question. I don't know that people have measured eye motions in mammals mainly, and a bit in birds. But so we're of the view that a lot of birds, probably with these, especially birds with eyes with larger lateral monocular fields, control what they're looking at by controlling their head motion relative to the eye motion. But that's a good question about fish. I don't know the answer to that.
Yeah, I'm just curious as to whether it sort of opens up any interesting problems or sort of would serve as an interesting model system for particular aspects of this.
Yeah. No, I think that since I have never, very, very rarely have ever worked on fish, I never thought about asking that question. So that's a good one, Giorgiano. Yeah. Henry.
Hey, great talk. I was wondering about, well, two things. One is the simplest question is these pigeons are making these rapid movements as they're sort of weaving through the poles. Do you know how close they are to sort of the limits of their ability to turn? And the other one is, have you ever done anything where the poles move to sort of see how they respond to a perturbation?
Yeah, that's the lot. We thought of trying to have actuated poles where we could move them and see how the animals would react to that. We never actually developed a system where we could implement that. There was a study that Dave Williams did when he was a postdoc with me, where we looked at we changed the spacing of the poles. So it was basically just a linear array of poles, and they had different widths between the poles. And we looked at how the pigeons, would they go through really narrow spaces, and how did they navigate through a narrow space versus a wider space. And it turns out pigeons will fly through spaces that give them 1 centimeter clearance on either shoulder. So they tuck the wings in, they either retract them. They had two different strategies. They had a wing fold position or a wing pause position. So they're flapping the wings and they hold the wings back like this, or they fold them back behind them. And they would go through the space with basically a centimeter clearance. I think it was it was 11 centimeters was the narrow, or 13 centimeters might have been our narrowest, and it's 11 centimeters from the left to the right side of the pigeon wing. And then wider spacings, they would so they'd adopt either this wing pause or this wing fold strategy, depending on the spacing. But they have a tremendous kinesthetic sense of their body position relative to the poles. Now, we did have pigeons collide with poles. There were instances where the pigeons would not make the right decision, and they collided with a pole. Not too often, but they did. I think it's hard to know what the maximum ability of the pigeon is in terms of its turning velocity, rate of turn. But so I think we were just fortunate they were, and we decided not, somebody, another way to vary the experiment would have been to had more poles in and create the spacing density of the poles. But those are all just hard experiments to do. We thought about looking into, for a while we did trials where we were interested in whether pigeons learn, what's the easiest path to go through. So we set up the poles at a fixed position and we'd fly them through and see whether they adopted how soon they would adopt a given flight path. And we didn't see a real rapid learning curve, partly because they were pretty successful, at least the density we had of 15 poles in that 3 by 3 meter spacing. that they basically didn't show. Either the pigeons are not that smart or they just don't have to worry about it. But those learning experiments are hard to do, so we ended up not really following through because it just takes huge numbers of trials, and the pigeons actually get tired. I mean, we're often running like 45 flight trials, so the experiments run a long time, and the pigeons have to fly back to the starting perch every time, right? So we move the poles out of the way, they fly back, and then we'd have to set them up again and then do another recording trial. So, but moving poles, as you know, basically again, where there's sensory cue that's moving, how do they detect there's optic flow to self motion versus the motion of an obstacle in the of its own movement would have been interesting to look at, but we didn't do that. Yeah, all good questions. I mean, there are experiments that are fun to think about doing, but often then hard to have the time to actually carry them out and be successful with them. Yeah.
Are there any other questions before we? I'm just noticing the time. I no wonder people have had to disappear. But are there any last minute questions before we close out? Okay. Well, thank you so much, Annie, for taking the time to talk with us. It was a really interesting seminar. Nice to see all those different projects coming together.
All right. Well, it's good back to. I think some people have heard some of this before, so seeing some of the faces that were or the names that were in attendance. But yeah. Anyway, nice to see you all, Giordano, and meet you, Alessandro, and take care, everybody. Yeah.
Thank you.
Okay.
Bye.